Welcome to my lecture series on main group chemistry. In my last lecture, I was discussing about the structure and bonding concepts used in main group chemistry. While discussing structure and bonding aspects, I had mentioned about VSEPR theory, and also I introduced the term steric number, and also I discussed the molecules having steric number 2 to 6 and 2 to 7. And now let me discuss on molecules having both bonded pairs and lone pairs. So, in case of steric number 2, there are no lone pairs, only bonded pairs are there. So, we can, for example, beryllium hydride or CO2, one can write the structure conveniently. In case of beryllium, we have 2 electrons here coming from 1 electron each. So, that means essentially 1 electron from hydrogen will combine with 1 electron from beryllium to form a covalent bond. Similarly, another electron from beryllium will combine with hydrogen to form BH bond. So, it is a linear geometry is there, and another example is CO2. One can also write using this method. So, linear geometry will be there, or one can also write something like this. In case of steric number 3, we come across 2 types of molecules having no lone pairs, that is BF3 or SO3. We can have 2 bonded pair and lone pair. In that case, examples are SO2 and O3. So, in this case what happens, essentially we have the central atom and we have peripheral atoms. Peripheral atoms have denoted by P, central atom A, and we have a lone pair here. So, this type of molecules will be there. So, they have bent shape, and here angles may not be necessarily 120, here it may be little less to accommodate this lone pair. These essentially less than 120, whereas this angle will be little more. And in case of steric number 4, we come across 3 kinds of molecules. One is 0 lone pairs, or having 1 lone pair, or having 2 lone pairs. Let us look into the molecules having 3 bonded pairs and 1 lone pair. The example is NH3 are all tertiary amines, and also the trivalent compounds of all group 15 elements such as nitrogen, phosphorus, arsenic, antimony and bismuth, PH3, tertiary phosphine, PCl3, PF3, ACl3, all are examples of having 3 bonded pair and lone pair and have a pyramidal structure. So, in this case N So, that means here essentially N has 3 covalent bonds with 3 hydrogens, and this unutilized lone pair will be occupying one of the positions. The here geometry is tetrahedral, shape is pyramidal. Okay. So, this is how one can write having 3 bonded pairs plus 1 lone pair, whereas steric number 4. Let us look into the steric number 4 having 2 bonded pairs and 2 lone pairs. Examples are plenty: water, H2S, SF2, I3 plus, etc. So, let us look into the case of water. So, this is how one can write the geometry for oxygen in water, showing the tetrahedral geometry. And here, while considering the shape, while deciding the shape of the molecule, one can ignore the lone pairs. So, it has a V shape or bent shape. The geometry is again tetrahedral and shape is bent shape. Besides other examples are H2S, SF2, I3 plus. Let us look into I3 plus. In I3 plus is interesting, one of the iodine will be central atom here. So, first let us count the number of electrons using Lewis method. So, here in counting, either we can count all the valence electrons of the central atom and just one electron from the peripheral atoms, or we can count everything and try to satisfy the octet. Either way one can write it. Now, I will show you just omitting all the electrons of the peripheral atoms, but considering only one electron that makes a covalent bond through sharing with the central atom. So, now we have I has 7 electrons and these two will be giving 2 electrons. So, 9 electrons. Since it has a positive charge, 1 electron has to be deducted. So, we have 8 electrons. That means, we have 4 pairs of electrons are there. So, this is our steric number. In this one, essentially it cannot have now this kind of linear geometry, it is not possible. So, this is wrong. So, this is how immediately you will come to know that this is not the right way of writing. So, now first write the central atom and put the lone pair here and put these peripheral atoms. So, this is the I3 plus. I3 plus, the central iodine has the tetrahedral geometry and it has 2 bond pairs and 2 lone pairs. So, if you do any mistake here, we should be able to correct it simply by looking into the steric number. Steric number will guide you in writing the precise geometry and also knowing the correct shape of the molecule or ion. Okay, let us look into Pcl 5. Pcl 5 has a trigonal bipyramidal geometry. Pf 5 can also be considered. So, here P plus 5 Cl. So, P has a total of S2P3. So, we have 5 electrons are there. It has S2P3 electronic configuration plus each chlorine is giving 1 electron. So, we have a total of 5 coming from 5 chlorines. So, we have a 10 electrons. We have a total of 10 electrons divided by 2. 5 is the steric number. Now, we know the steric number is 5. Now, with steric number 5, the geometry that is supposed to be considered is trigonal bipyramidal. And now, place so this is how we can write the structure of Pcl 5 molecule which has trigonal bipyramidal geometry. Let us look into another case of steric number 5, but having 1 lone pair and 4 bonded pair. The example that I have given is SF4. Let us look into the SF4 molecule here, how it will have that kind of structure and shape. So, in case of SF4, we know that steric number is 5. So, let us determine that one. We have 6 electrons are there from sulfur because it is S2P4 similar to oxygen, and 4 electrons are coming 1 each from fluorine atoms. So, it is 6 plus 4 equals 10 by 2 equals 5 is the steric number. In this one, what we have is 4 SF bonds are there. So, 4 bonded pairs are there plus 1 lone pair is there. So, first let us write the geometry and then we should consider where this lone pair should be positioned. Okay. So, now we have two options. One is we can place lone pair here, or we can keep in the axial position. If you keep the lone pair in axial position, it makes angles of 90 with all the equatorial atoms, whereas if you place here, it makes 120 angle with the 2 and 90 degree with the 2. So, by placing this one here, the molecule can gain extra stability, and also lone pairs can get more space to be positioned here. As a result, SF4 has this kind of structure. So, this one it appears like seesaw. That is the reason always the shape of SF4 is recognized as having seesaw structure. Of course, it is not exactly having a seesaw structure. Essentially, they are little bit bent to give more space for these lone pairs. These are little bit bent towards away from their mean position. This is the actual structure of SF4 molecule. So, in case of ClF3, we have a different situation. We have steric number is 5, but we have 2 lone pairs and 3 bonded pairs. Let us try to calculate and see whether it is correct or not. ClF3, the central atom is chlorine. So, chlorine is contributing 7 electrons, and fluorine atoms are giving 1 electron each. So, we have again 10 electrons total, and steric number is 5. So, now again the geometry is trigonal bipyramidal. So, now we have 2 lone pairs. Taking the hint from SF4, it is convenient to place them in equatorial position so that the repulsion can be minimum. So, we shall place here lone pairs, and remaining fluorine atoms can be placed to axial position, one in equatorial position, and here the geometry is trigonal bipyramidal. Shape is, if we ignore this, it appears like T molecules. The shape is T shape. So, this is how it called as having T shape. Essentially, so these are not considered. So, it appears like having T shape. So, this is how one can also write correct structure for ClF3, showing 3 bonded pairs and 2 lone pairs. Another case is, in case of steric number 5, is having 3 lone pairs and 2 bonded pairs. Example, I am going to consider here, of course, I have given examples of XCF2, xenon difluoride, and IF2 minus and I3 minus. Let us look into I3 minus. We discussed I3 plus, let us look into I3 minus now. So, in I3 minus, let us count electrons. We have 3, and the central one will be one of the iodine. So, that will give 7 electrons, and remaining 2 iodines will give 1 electron each, and plus we have a negative charge. So, total again 10 electrons are there. 10 by 2 equals 5 is the steric number. So, here what we have is 2 bonded pairs are there, because we have 2 II bonds, plus we have 3 lone pairs. First, let us write trigonal bipyramidal geometry as we wrote before. So, this is how we can write. And now, to minimize the repulsion between the lone pairs, what we should do is we should place all the lone pairs in the equatorial position like this, and remaining 2 iodine atoms can be placed here, and this is the structure of I3 minus. So, here again it is geometry trigonal bipyramidal shape linear. Okay. And similarly one can write IF2 minus, and also in case of XCF2, let me consider XCF2 as well, because here we have more lone pairs, and XCF2 this has 8 electrons, S2p6 electronic configuration. So, we have 8 electrons and 1 electron each is coming from fluorine. So, we have again 10 electrons, 10 divided by 2 equals 5 is the steric number, and in this case we have 2 XCF bonds are there, 2 XCF bonds are there, and we have this is bonded pair and 3 lone pairs are there. So, geometry is again trigonal bipyramidal, Xc at the center, so XCF2 is geometry is trigonal bipyramidal shape so one can write by using this VSEPR theory for any given molecule correct structure and understand the geometry as well as the shapes. So, let us look into the steric number 6. In this one we have 3 cases having no lone pair. When we have no lone pair, example I am going to consider is sulfur hexafluoride. So, sulfur has 6 S2p4 electronic configuration. So, it is contributing 6 electrons and 6 fluorine atoms are contributing 1 electron each. So, we have a total of 12 electrons divided by 2 equals 6 pairs of electrons. So, 6 electron pairs, this is our steric number. So, steric number is 6. So, in this one all are bonded pairs. So, the standard geometry is octahedral. So, the geometry is octahedral here. Now, let us consider another case where we have 1 lone pair and 5 bonded pair. Example is IF5. So, let us look into IF5 here. The steric number is 6, IF5. So, they are called interhalogen compounds. There are plenty of interhalogen compounds are there, neutral, anionic as well as cationic. I will be explaining more details about their preparation, all those things when I discuss the group 17 elements. Now, let us look into IF5. In case of IF5, the central atom is I, giving 7 electrons, and then each F is giving 1 electron. So, it becomes 5. So, totally we have 12 electrons, that is which is equal to 6 pairs, that is our steric number is 6. So, now out of this one we have 5 IF bonds are there, that is bonded pair, and then 1 lone pair will be there then. So, geometry is octahedral as usual, because the steric number is 6. So, first let us make 5 IF bonds, 1 here, 1 here, 1 here, 1 here, 1 here. Now, the lone pair will come and sit here in one of the axial position. Now, if you just look into it, the geometry is octahedral. shape square based pyramid. So, these are the examples where we have a lone pair, and as a result we are seeing the square pyramidal shape for some of these molecules having steric number 6 with one lone pair and 5 bonded pairs. Another example is BRF5. Let us look into the last one in the series, octahedral molecules with steric number 6 having 2 lone pairs and 4 bonded pairs. Example considered here is XeF4. So, in case of XeF4, again S2p6 electronic configuration is xenon. So, we have 8 electrons and plus 4 fluorine atoms are giving 4 electrons. So, we have a total of 12 electrons, that is equal 6 will be its steric number. In this one we have 2 lone pairs and 4 bonded pairs, because we have 4 XeF bonds and 2 lone pairs will be there. The geometry is again octahedral, xenon will be at the center. These are placed here, and in the axial position 2 lone pairs will occupy. So, now the geometry of XeF4 is octahedral, whereas the shape is square planar, except those cases where we come across 2 lone pairs in the axial position. We do not have any examples among main group elements that show square planar geometry. Square planar geometry is seldom shown when we have 4 bonded pairs. The preferred geometry is tetrahedral. Similarly, one can also look into IF4 minus. In case of IF4 minus, again I is giving IF4 minus, I is giving 7 plus fluorine atoms are giving 4 and plus 1 electron is there. So, 12 electrons are there, again the steric number is 6. Again the geometry is octahedral, and all the IF bonds will be in the plane giving a square planar shape. The geometry is still octahedral. I think this all about valence shell electron pair repulsion theory. It is quite successful in predicting the molecular geometries of main group compounds, but only in few cases it fails to predict the shapes of isoelectronic species and also transition metal compound. That means, when we have isoelectronic species and also when we are considering transition metals where we have inactive lone pairs, VSEPR theory does not give a right geometry and shape for those molecules. And another limitation of valence shell electron pair repulsion theory is it does not consider the relative sizes of substituents, and as I said, stereochemically inactive lone pairs into the consideration. As a result, what happens, one needs to look for a different bonding concept for especially explaining the bonding in transition metal complexes. So, of course, in case of transition metal complexes, 3 theories have been successfully used. One is valence bond theory, another one is crystal field theory, and another one is molecular orbital theory. And in case of crystal field theory, we always talk about the ligands and metal ions as point charges, and the interaction between the metal and the ligand is purely electrostatic in nature. And if the metal is cation and the ligand is anion, it is ion-ion interaction. If the metal is cation and ligand is neutral, it is called ion dipolar interaction. But we come across a situation where the metal is neutral and ligand is also neutral. For example, if we consider nickel tetracarbonyl, chromium hexacarbonyl, iron pentacarbonyl, where metal is neutral and ligand is neutral, in that case what happens, we have to consider the electrostatic interaction of dipolar in nature. However, crystal field theory does not explain the electrostatic interaction that exists between dipolar and dipolar species. As a result, crystal field theory fails to explain bonding in metal compounds having metal in their zero valence state. In those cases, in order to explain dipolar interaction, some allowance is made and that is called ligand field theory. So, ligand field theory explains all three kinds of electrostatic interactions, and of course, once when we go to more refined method or theory, molecular orbital theory, that can explain almost all aspects of all compounds without any controversy or without any problem. In my next lecture, I will be focusing your attention on another important theory, valence bond theory. Valence bond theory is essentially refined from the valential electron pair repulsion theory, introducing the concept of hybridization proposed by Linus Pauling. In my next lecture, I will be discussing about the valence bond theory and its application to the compounds of main group elements. Have a pleasant reading, and thank you very much.